Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, is that a robot testing robot? And how does that thing work? Hello everyone, welcome to Robot Talk. I'm your host, Claire Asher, and this week we're returning to the topic of space robotics. This time, focusing on robots that perform important tasks in orbit, from repairing damaged satellites to producing new products. Before we get started, I'd like to remind you to subscribe to Robot Talk through your favourite podcast provider to make sure you're the first to hear the latest episodes. Another way to find out about new episodes is the email newsletter, which you can sign up to by going to robottalk.org. So, without further ado, let's get on with this week's interview. I recently had a fascinating discussion with Jeremy Hadall from the Satellite Applications Catapult about robotic systems for in-orbit servicing, assembly, and manufacturing. This week, I'm chatting to Jeremy Hadall, a robotics development lead at the Satellite Applications Catapult, whose work focuses on in-orbit servicing, manufacturing, and assembly. Hi Jeremy, welcome to Robot Talk.
Hi, thank you for having me.
So, first of all, can you tell us a little bit about the Satellite Applications Catapult and what it's all about?
Yeah, absolutely. So the Satellite Applications Catapult is one of 9 catapults that we have in the UK. And we have catapults that deal with manufacturing, digital technologies, connected places, cities, energy, lots of others. And we focus specifically on the space industry. And in the UK, it's quite a big industry, although the actual number of people working in space industry is quite small, but the actual industry itself adds something like £350 billion to the UK economy annually. Wow. And that covers everything from things like sat-nav, weather, communications, defence, climate monitoring, even just beaming Netflix into our homes. It's all that kind of stuff. And we're the 4th largest contributor to ESA. So in the Catapult, we support the whole of the UK industry. And in my area, we particularly support that field of in-orbit servicing, assembly and manufacturing, or ISAM as we tend to call it, because it's a bit of a mouthful otherwise.
Yeah.
And so what that means is we look at how do we assemble new structures in space, and that might be space-based solar power stations, new spacecraft, new space stations, big antennas, big telescopes, whatever that might be. We're starting to look at how we manufacture things in space, because there's some interesting things that we can do in the space environment that you can't do on Earth.
Okay.
Particularly around pharmaceuticals and silicons. And then we look at how do we support the in-service fleet of spacecraft. So how do we refuel them? How do we keep them operating in space? And those last 2 are really important because historically we haven't done that. We've just left them in orbit.
Yeah.
And that started to create a lot of debris and litter, if you like, in orbit, with lots of dead satellites and bits of spacecraft that have come off. And that creates a bigger problem in that those things can then crash into other satellites. They could fall back to Earth. So we're trying to help the industry be more sustainable and ultimately safer. So we cover debris and removal, and space is, it's the epitome of remote and challenging environments. It's somewhere where an astronaut or a human really is under a lot of pressure. The environment is trying to kill them in lots of different ways, all at the same time. So really, we need robots to go and do that because it is dangerous. It's also very expensive and complicated to send humans. And there aren't many humans that are certified, qualified, whatever you want to call it, that can actually go into space. So in a planet of 8 or whatever it is billion people, there's only 600 astronauts active. So we really need robots to go and do it.
Yeah. The point you made about manufacturing is really interesting because when people say in orbit manufacturing, I always sort of think, oh, well, it's obviously makes a lot of sense to manufacture things you need in space. I never considered that you might manufacture things that you need on Earth and then bring them back.
Yeah, so that concept of making stuff in space or manufacturing things in space and then bringing it back to Earth is really new, and we're just starting to see people start doing that. But like I say, you could do things in space that you can't do on Earth. You can mix oils and waters together, which is it's really hard to do that on Earth, but in orbit it's much easier. You can make perfect spheres, absolutely perfect spheres in space. And then there's this kind of strange concept where on one side of a spacecraft you can be at 150 degrees centigrade, but on the other side of the satellite you can be at minus 250 degrees centigrade. And if you can transfer your material between the two, you can get really rapid heat transfers and heat changes. So there's some really interesting concepts, and for, I say, for pharmaceuticals, it's a super clean environment to do drug discovery work. For silicon chips and the next generation of chips for quantum computing, it's really exciting and important that we can do stuff up there. So we're really on the cusp of understanding what we can do and how we then get it back to Earth to use it on Earth.
That's fascinating. So yeah, as you mentioned, you're leading robotics development in the ISAM testing facility.
Yeah.
So what exactly are you doing in that test facility, and what kind of robots do you work with?
So we're based at Westcott in Buckinghamshire. As you say, it's an ISAM test and development facility. And ISAM covers a lot of different areas, but for the robotics point of view, we have two functions. We're here to provide a realistic environment, or as best we can, provide a realistic environment on Earth as we do in space. So we have quite a large space that we put the robots in. We can, as best as we can, make that feel like the orbital environment. And that helps companies test their sensors, their navigation systems, their planning algorithms, their manipulators, their end effectors, before they actually go through a full launch test campaign, because that's very expensive and you only get one chance to do it. We can do it several times. And our second function is to support companies do their research and development. So we either do that for companies or we do that collaboratively with companies. And there we develop technologies that might be too new or maybe too risky for them to do on their own.
Right.
Or maybe they want to look at something that they don't really have the capability to do, or it might be too difficult for them. We can do that. And then that leads on to prototyping and into potentially a spin out or potentially into new products and services that they can sell. So we have three principal capabilities to do that. One is our ISAM yard or ISAM facility. It's essentially just a very big black room. So it's 27 meters long. It's blacked out completely. So everything is painted black. And that's not because space is dark. Space is absolutely not dark. It's actually a very bright place. But we want everything in there to disappear. We want our robots to disappear into the background, because the things we're interested in are what's on the end of our robots. So somebody else's robot or somebody else's robot technology. So we have two industrial robots. They're off-the-shelf KUKA robots. We just don't use them as they were intended to be used. So that always causes us a few headaches. One of them is static and one of them is track-mounted, so we can move that one up and down the room. And what we do with those is we mount satellite technologies or robot technologies or a combination of technologies on the two robots and get them coming together as if they were flying in space. So we're just trying to simulate that orbital environment and how those two things would come together using our ground-based robots. So to some extent, we're trying to use them as rocket motors and simulate how they work in orbit.
Yeah.
We have a motion capture system, so we can see where everything is going. We can track it and give some real interesting data back to our clients. We can change the lighting. So although it's very dark in there when we have it all the lights turned off, we have the ability to shine very bright lights in certain places and get that light to move around. And we do that to simulate the sun and the way the sun moves around in orbit. We have something called a gravity offload system, which is a new system that will come on stream at the end of March. And so one of our biggest problems in orbit is if you touch something in orbit and don't grab hold of it, the force you imply as you touch it is going to push that thing away, and it's just going to keep going because there's nothing to stop it.
Right. Yeah.
So the offload system attempts to remove the effect of gravity on Earth by replicating that motion. So if I move one of my robots up to it, it touches the object. It might be a satellite or something else. It will then move away at a speed that's related to the force that we're pushing on it. So that's a big step forward for us. And that also refers to something we call contact dynamics. So we have two very large KUKA industrial robots. They're designed to build cars. They're not designed to be flexible. They're not designed to be pushed around, but we hack them a little bit, and it enables us to actually have that contact dynamic. So when they come together, we can get them react as if it's almost like a gravity compensation mode that you would have in a collaborative robot.
Right.
We replicate that in a robot that's actually carrying 120 kilos and isn't supposed to be able to do that, but we can replicate that. And then to make them all move like a spacecraft, we have a fairly complicated software stack that connects something we call attitude orientation control system. It's basically a navigation system for a satellite, but that links into our robot controls, and it makes the robots move as if they were satellites. So instead of going in straight lines or what you would see as familiar robot motions, they move as if they were satellites.
Okay.
So that's one part of the facility. We then have the playground, which we like to call it, which is a much smaller lab. There we can go and try different things out with smaller robots. And the important thing about those smaller robots is, although, again, we're using universal robots, so off-the-shelf common robots that you'd see across industry and academia. But the interesting thing about those is they're very, very similar kinematically to the robots that we would actually use in space.
Okay.
And the reason for that is that kind of design lends itself to packaging it inside a spacecraft. It folds up quite nicely. It's quite easy to service and maintain it. You can swap bits in and out on not necessarily universal, but on the designs that we see. That design lends itself to that approach. And because they're universal robots, we can do lots of things with the control system. So we're trying autonomous assembly tasks, virtual reality control, teleoperation control, deep reinforcement learning with them. So there's lots of neat things we can do with those robots that we're trying. The next step, which is about assembling and servicing spacecraft in orbit, where there's no one there to help you do that. So the robot has to be able to do it and has to be able to do it on its own. And then the last part that wraps all around the other two is our big virtual environment. So although we have these big physical test facilities, we do a lot of work in simulation using NVIDIA Omniverse and ROS, simply because when we get to doing testing, we want to know what these things are likely to do.
Yeah.
And that's quite important because some of the spacecraft equipment that we will mount on the end of the robots can be really, really expensive.
Yeah.
And it's almost one-off. You don't want to find out that your robot is going to do something strange and drive that thing into the wall or into another robot. So you want to know that before you, as much as you can, know that in simulation. But it also means that we can run multiple training routines, multiple tests in the simulation whilst that thing is being built and designed and fully validated for flight. So we don't always have to have it there. We're having a discussion this morning and somebody said, we only really need the physical bits so we can have that nice, give the humans that nice, warm, fluffy feeling that everything works. Because in reality, we can do it all in the simulation. And the other good thing about that digital operation, and we can do this with the physical operation as well, is we can link it with different systems. So we can have a VR, AR control room somewhere. It doesn't have to be on site. We can have a full mission control room somewhere completely else. We can have the satellite control system on a different site, and we can link all of those things together as a federated system. Okay. And they all operate together, but we can do all of that in simulation and be sure they're all working before we commit to putting them on the robots. So the simulation that virtual environment is a really, really important part of the whole capability we have. I think we spend equally as much time on that as we do on the physical things now.
Yeah. So, I mean, I think you talked a little bit about the logic for this, but it's kind of slightly surprising to me that you're using sort of off-the-shelf, commercially available robots for such a bespoke task.
Mm-hmm.
I guess developing your own robots for these tasks from scratch would be too expensive and time consuming, or?
Yeah, you're right. It's absolutely about timing and expense. So if you look at what we've done in terms of in-orbit servicing, assembly and manufacturing robotics previously over history, there's 2, maybe 3 that have been built. And the first one was on the space shuttle, and it was Canadarm1. The second one is Canadarm2, now on the ISS. And then there's the European robotics arm, and there's the Dextry, which fits onto the Canadarm, and then there's a Russian variant. But they're all very big, and they're all very, very expensive, and they take a very, very long time to build and to operate. And they're very expensive to operate as well. But that's the other big problem. And those robots are designed for space. And one of the reasons we tend to use industrial robots or earthbound robots is we have this annoying thing called gravity. I mean, gravity is quite useful, but when you're talking about robots in space, it's actually it's not there. So if I used a space-rated robot on Earth and hung a payload or a weight on the end of it, gravity will eventually pull it back towards the ground because we don't have any brakes in the arms. Because in orbit, we don't need them because we have a microgravity environment where the effect of Earth's gravity is so small, it just stays in one position. So that's one reason why we use them. I say it's very expensive to build and develop these robots. It takes a very long time to build them. And also, they're bespoke items. So although we use the Kukas and the Universals in a way that they're not designed to be used, and we do things with the control systems that when you talk to Kuka and Universal, they go, "Oh, that's very new," and that's quite a different way to do it.
Yeah, it's
easier to do it than to start from scratch because we've got a kinematic model, we've got a physical model we can work with rather than having to build it all from scratch. So that's why we do it that way.
Yeah. So, can you talk a little bit about some of the latest robotic systems that are being designed for in-orbit servicing and manufacturing tasks?
Yeah, well, as I said, there are maybe 4, maybe 5 robots that have gone up and done this in orbit. I think when most people think about robotics in space, they kind of think of the planetary rovers, the Perseverance, Curiosity, like even Wall-E robots.
Yeah,
they're kind of very expensive, bespoke one-offs. And even the robot manipulators, the arms that have been launched are very similar. So the main focus of robotic systems now, or the future of robotic systems in orbit, is smaller robots. Like I say, they look a little bit like a universal robot, most of them. But they're cheaper to launch because they're lower weight. They're cheaper to operate. And we've only started to see that in the last 5 or 6 years that those kind of robots have started to come to the fore. But even then, we've probably launched 1 test mission, or what we call an in-orbit demonstration.
Okay.
And that was launched by a company in the US last year. And it's the only one that's gone up and done it. But there are lots of people working on this and lots of people looking at it. But all those robots kind of have the same design. Obviously, the materials we're using are slightly different. The electronics we use are slightly different just because of the space environment. But they're not that different. They're fairly similar. And then I guess the next step for us is looking at the control side of things. So how do we have open architectures for modularity? How do we build robots that can do multiple tasks and maybe even change themselves to do different tasks, whether that be their end effector or their tool changes or even their entire structure? How can we build that modularity into them? And then how do we build the autonomy into those systems? Because I say there's 500, 600 qualified astronauts, and in orbit there's maybe a dozen at any one time maximum across the ISS and the Chinese space station. So there aren't many. And we don't necessarily want them to be spending all their time controlling these robots. And similarly, we don't want lots of ground controllers using the robots just because it's not a useful use of their time, but also you have a latency issue. So if your robot's quite a long way away from us, you might have a latency problem. That's not so bad to the space station because it's only 400 kilometers away.
Yeah.
it's not so bad to a geostationary satellite, which is about 37,000 kilometers away. That's about 0.1 of a second, maybe a bit less in terms of delay.
Okay.
If you go further away, that delay starts to increase quite a lot. So the moon is about a second. Mars can be anything up to 40 minutes, depending on the orientation of Earth and Mars. So that autonomy and not relying on humans is really important. But then you get into, how do you make sure you trust the robot to do what it says it's going to do? How is the robot going to know what it's going to do? And what happens if it gets to a situation where it says, I don't know what I'm supposed to do? Do we want it to stop? That might have some very dire consequences. Or do you want it to make a best guess? Or, what's the next thing? So all that autonomous control and autonomy is a challenge. And the space industry is quite conservative around this kind of stuff. It likes to know what's going to happen when it does something. Yeah. So that's a big challenge for us.
Yeah. I guess, you hear about problems with autonomous vehicles on Earth where they just can't get enough data to cope with edge cases. I imagine in space that's even more challenging.
It is, because I say, if your edge case is something that you haven't predicted and been able to build into that robot's algorithm set, what do? Do you wait for a human to input? It might be too late. Do you ask the robot to make a best guess and hope that it's going to make the best guess? So it's a big challenge. And another aspect we have with this around autonomy is making sure that the robot's got the power to do what it needs to do. Getting those power to the robot is quite critical. We're very reliant on the sun. Yeah. And that's fine if we're actually pointing at the sun, but if we're on the dark side of the moon, or even if we're in low Earth orbit and we're the wrong side of the planet as the planet is orbiting, you won't have the sun. So you're then relying on whatever battery power you've got. Yeah. And your robot's still got to operate. It's still got to do those tasks. It's still got to be able to understand what's going on around it, understand the state of the satellite, understand the state of the robot, understand what it should do, and then make a decision and do it, and then prove that it's done it to you. So all of those things are quite a big challenge. And like I say, the space industry is very conservative. It wants to know what's happened, and quite rightly so. So it's a challenge. And that's before you start bringing humans into this as well. So if there's a human anywhere near the spacecraft in orbit, then it's another whole layer of safety we have to build in to keep those people safe. Yeah.
So it's likely to be like a slow development process of these kinds of technologies then?
Yeah, probably. Having said that, though, there's a real desire to accelerate the development of all of these kind of technologies, and it's driven by it's not driven necessarily by sustainability, because the space industry and sustainability haven't always gone together very well. It's kind of, I'm not a space industry guy, so I can kind of get away with saying this, but the space industry haven't really thought about what happens with satellites when they stop working. It's like, well, space is massive, okay, so we can just leave it there and not worry about it. Well, you can, but if it starts to fall back into Earth orbit, that might have some environmental impacts, and it might crash onto somebody's house. And if it doesn't, it's still blocking bits of space that you might want to actually go and use. And if it gets so bad, we might end up with so much up there that we can't get to certain parts of space. So the industry hasn't really thought about it. So there's a real drive to kind of think about that. But then the other driver is quite simply it's SpaceX. It's the fact that they are now able to launch so many satellites at such a regular cadence. The cost is coming down all the time. And although Starship hasn't been fully successful yet, it's just a matter of time before we can launch 150 tons of payload into orbit. And once you're there, the cost of launching just absolutely plummets. And then you have a real challenge, because it's a case of, well, shall I just launch something else and not worry about it? Space is huge, right? I don't have to worry about all that debris. I can just launch something for $1,000 a kilo and it's really cheap. Yeah. Or do you say, well, okay, you can do that, but actually we need to go and start tidying up behind us? And so all of that is quite a big driver for it. So the economics of space, the sustainability of space, and there's quite a few people who are saying, look, we if we don't do this now, we run the risk of in 20, 30 years finding ourselves in a very similar situation to plastic in the ocean.
Yeah.
I'm not sure it's quite that bad yet, but it's a big driver. So parts of the space industry want to go very slowly, and then you get lots of startups and very keen people want to go very fast and go, let's just go fail fast. And SpaceX are, they do that very quickly. So everybody's looking at SpaceX and going, yeah, let's go fail fast. It's really great. And that's going to drive development quite quickly. So it is accelerating, but it's still quite slow.
Yeah. That car that's now orbiting Earth, is that causing problems? It's a pretty big chunk of debris.
Yeah, it is a pretty big chunk of debris. It's not the biggest chunk of debris orbiting Earth, but there's some pretty big satellites that they're no longer working. That there's one that's about 10 tons that's orbiting. That's
wow.
A bit of a problem. But yeah, the Tesla Roadster, it's just part of the debris that's up there. And when we talk about debris, we're talking about everything from watches, cameras that astronauts have dropped, toolboxes. There's a video on YouTube you can see where the astronaut just accidentally drops the toolbox and it just floats away. And you hear ground control saying, "Oh, you've lost the tools." And the astronaut says, "Yeah."
Yeah.
And that's been the attitude for a long time. But it goes right up through the Roadster, the car, through to rocket bodies, dead satellites. There's some really big stuff up there. The numbers are quite scary. It's something like 36,000 objects that are about 1 meter squared. And it jumps to over 1 million objects when you get down to about between 1 and 10 centimeters. And after that, you can't really track anything, but it's estimated to be somewhere in the region of 130 million debris items.
Oh my gosh.
And it could be anything.
Yeah.
And some of these will cause damage. There's actually a hole in the side of the Canadarm on the ISS that was caused by some debris. Now, we don't know if it was a natural debris, so a micrometeoroid. There's lots of those.
Right.
Or if it was something else, but it's there.
Yeah.
And on the ISS, there's scratches all over the outside of the ISS. I was told one today, somebody said, well, yeah, an astronaut went out in his spacesuit, he came back in, he had a big gash in the glove, and they couldn't work out where the gash came from. And they figured out eventually that one of the handrails had been hit by something and just scratched all the paintwork off, and it had just gone straight through the glove. So the debris is starting to become quite a big issue.
Yeah. It's quite terrifying, like, when you imagine what it must be like to be up there. And like you said, the environment is trying to kill them. So.
Yeah. But the other interesting thing about it is, so far we've said it's all a problem in space. Some of this stuff will fall back to Earth. And where's it going to fall back? If it's controlled, we can bring it back to somewhere where it's relatively safe. So the middle of the Pacific is a favorite place to put some things.
Yeah.
If we're not controlling it, it could just go anywhere. And some of the materials that have been used, they're not materials that we'd really want to be burning up in the upper atmosphere and making that problem even worse. So it all becomes a bit of a challenge. All of which says we need more robots in space to clear it all up.
Yes.
Which, from my point of view, is a good thing.
Yeah, keeps you busy.
Yeah, it keeps me busy. So,
prior to working in the kind of satellite area, you used to work on robotics for manufacturing and logistics here on Earth. So do you want to tell me about some robotic developments in those areas that you are particularly excited about?
The ones that always excited me were around how do we get robots to do more than one task. So typically what a robot in a manufacturing plant will do, and this is changing, but it would just do one thing. And the whole system would be designed to allow it to do that one thing, and it would do it really, really well, highly repeatably. In a car plant, it might be 60 times an hour, 90 times an hour, whatever the rate was. So it was really fast, and even faster in a food factory or a logistics facility. That's great, but you have one machine doing one thing. Not all manufacturing is like that. In fact, in the UK, very little manufacturing is like that. So how do you make that robot do several things as well? And that was always a big challenge. So that was the one that always excited me, about how do we get that to do that? What's the systems we need to use? Is it some sort of dexterous manipulation? Is it some sort of autonomy or decision making? Do we need human-robot interaction? That was another one that always excited me, is how do we get humans and robots working together in the same environment? And that's still a big interest of me, but how do we do that in space? That's just another area.
Yeah.
I guess the one that I'm a little bit of a skeptic around humanoids, I have to say. We're not fully bought into why we should need humanoids. We design our environments to suit us, but we're not necessarily the most effective or efficient things in a manufacturing or logistics plant.
Yeah.
So why do we not design the environment to suit something else that's going to do that task much, much better than us? And I think the one that always gets me is the dishwasher. And if you look at a dishwasher, it's not a sink. It's not a sink and a mop and a cloth.
That's true.
It's completely different design.
Yeah. And
it probably washes those dishes far more effectively and potentially far more efficiently than you could do in a sink. But it's not designed like a sink. So why do we keep designing robots to go into manufacturing plants that look and act like humans? Why don't we design the manufacturing process and the plant and the robot in conjunction to be super efficient? Now, if that's a humanoid form, great. But a lot of times it's not a humanoid form.
Yeah.
So that's an interesting part of me. And I know a lot of people are going to go, no, humanoids are the way forward. No, I'm not so sure.
Yeah, I tend to agree with you. I think the main case I can see for humanoids is like if they're actually interacting with humans in a social way.
Yeah.
But yeah, your dishwasher example has given me like an image of like a very Wallace and Gromit style robot, like robotic arms doing the dishes for you.
It is that kind of thing. Is I think just because we can design robot arms to do tasks for us, it doesn't mean we should. We should probably think about what the task we're actually trying to do is, and then design the most efficient thing to do that task.
Yeah, absolutely.
But again, with the humanoids, we're just talking about washing dishes. If we wanted to do multiple things, then it does kind of lend you to go back towards the human form, because we are very adaptable and can do lots of different things. We don't necessarily do them very efficiently all the time, but maybe that's where we should head back towards in those situations.
Yeah.
I think robot designers need to think about what's the task you're doing and what's the most applicable robot. And we have the same in the space industry. We quite often think, well, okay, we're going to need a robot arm to do this task, and it's got to have some very dexterous manipulator on the surface of the satellite. Actually, it might not. It might be the case that what we really need to do is get a robot that looks more like a snake and goes inside the satellite to do something, rather than trying to service it from the outside. Maybe put something that goes inside it and fixes it from the inside out. So it's about choosing the right design for the right application.
Absolutely. Jeremy, it's been great speaking to you today. I've been talking to Jeremy Hadall from the Satellite Applications Catapult. Thank you.
Great, thank you.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And make sure you check out @Robot Talk Pod on social media to see a photo of a robot being used to simulate a satellite refueling operation at the ISAM test facility. I'm taking a break next week, but I'll be back after Easter with more fascinating guests. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.